All right. So let us start with this event now. I'm Aditya Jyotipal. I would be your host for this beautiful evening. Today's event is called Explaining AI from Regression to Computer Vision. Those are actually two of the hands-on demos which we will be doing at the end of this workshop or event today. So on screen you see some of the organizations I had the fortune of working with. Cognitive Applications Research Lab is a team in SRMISC. I was one of the founders of this team and the current team lead. I worked for a while as an intern with Samsung Research, as a technical head for WorldScript. I was an Explore ML facilitator, and today's event is Pi and AI. So, why not start this event by a talk by Andrew Ng? He is also the founder of DeepLearning.ai.
Hello, Deep Learners. I'm Andrew Ng, founder of DeepLearning.ai, and I'm excited to welcome you to our global deep learning community. I know that many of you are here today because you want to break into AI and build your career. I hope that being part of this community will help you to do so. To give you a proper welcome, I'd like to show you around the DeepLearning.ai offices and meet some of the teams so that you can see where it all happens.
Oh, hi, Andrew.
Do you want to tell our friends at Pine AI what you do at DeepLearning.ai?
Sure. Hi, everyone. I make articles and other media that help people learn about AI and help them understand the huge impact that AI is having in the world. Today, I'm putting together the next issue of The Batch, our weekly newsletter, and I'm looking for the biggest stories of the week to keep our readers informed.
What's been the most surprising thing you've run into working on The Batch?
How much is going on in this field? There is never a dull moment. You might think from the outside that machine learning engineers really understand everything about AI, but nobody understands everything about AI because this field is just coming to life right before my eyes as I put this thing together every week.
All right, I know you're really busy, so I'll let you get back to it.
Thanks. See you later.
Let's go meet Kian, who helped me create the deep learning specialization. He's working on an exciting new project. Hey Kian, so do you want to tell the people at Pine AI what you're working on?
Yes, sure. I'm leading a project called Workera, focusing on helping people get offers in AI and navigating their career by testing their skills, preparing for interviews and certifying them, as well as matching and referring them to good jobs in AI.
That's really cool. And what's the most exciting part of your day?
You know, the AI field is new, organizations and jobs are still misunderstood. So I'm excited to help people understand what different types of jobs exist in the field, what tasks they will work on, and what skills are needed to achieve those tasks.
Yep, and that's really important work. Well, it's nice chatting, and now let's go chat to Hotel, who is on their product team.
Hey, Andrew.
Do you want to say hi to our friends at Pine AI and let them know what you're working on?
I would love to. Hi, everyone. I lead the product team in DeepLearning.ai, where we create AI education content accessible to people all around the world. People like you.
And what are you most excited about right now?
I am so excited to see our community grow and to see how eager people are to learn more about AI.
Thanks, also.
Thanks, Andrew.
So, as you can see, our team is working hard to support you and help you learn. It's never been easier than before to break into AI. So if you want to build a career, you can leverage online resources available, including open source code, datasets, papers, and online courses like a deep learning specialization on Coursera. As part of this journey, I hope you get your hands dirty too. Don't be afraid of diving in to build your own project, or go ahead and try to replicate a research paper that you're excited about. One thing that I've seen help a lot of people succeed is if you can build a community or find a community of fellow deep learners you can meet with and study with on a regular basis. In fact, I hope that this Pine AI meetup that you're at right now will be a good place for you to meet these people. I hope you enjoyed the event today. and that you learn a lot, both from the talks and from each other. And once again, welcome to the deeplearning.ai community.
All right, so I really hope that you found this video quite interesting. Today's agenda is we'll be starting off with a brief discussion about the philosophy of AI, like what AI really is, how we understand it right now, and how the field has evolved since 1950s. And then we'll be talking a bit about linear regression, neural networks, the various forms of AI which exist. In the final part of our workshop, we would actually be implementing linear regression in three separate ways and compare them, like which way is better or which way is more robust, etc. We'll also be actually dealing with some object classification, and we'll be seeing what the neural network actually sees at every layer of the neural network. Don't worry if you do not exactly know what a neural network is right now. We will definitely know about more about it in the upcoming slides. And finally, we'll be having some doubts clearing and some closing comments. So I'm really excited to be here with you all. Let's go to the next slide. So what is AI? Artificial intelligence or machine intelligence is intelligence demonstrated by machines. So they try to mimic our cognitive abilities like perception, learning, planning, understanding, reasoning, etc. Is my screen visible for all of you? Alright. So it also talks about computer vision, natural language processing. Pretty much all of you must have heard about some of these topics as we go on and on. Now, before we speak more about AI, it's important to actually know about how this field started off. So, can any of you recognize the people on the screen? This would be really interesting. How many of you can recognize the four people on screen? Just go ahead. You can type it in the chat section, or you can unmute your mics and uh, say the answers. Don't be shy. I want the meetup to be as interactive as possible, so that you guys feel free to chime in and answer the questions, talk about what you want to, etc. Any of you know? All right, some people are still joining. Those of you who are still joining, if any of you know about those people who are on screen, do type it in the chat section so that we can go on. So, for example, the first person on screen is Alan Turing. He is often regarded as the father of theoretical computer science and AI. The second person is John McCarthy. He is also known as the father of AI. Marvin Minsky's work in the field of AI has been really interesting, and Lass is raised over it. So, artificial intelligence is the simulation of the functions of the human brain, such as visual perception, speech recognition, decision making, language translation, all by man made machines, especially computers. The field was started by Alan Turing, the first person on your screen, shortly after World War II, and the term was coined in 1956. The term artificial intelligence was coined by John McCarthy in 1956. At that time, he was a cognitive computer scientist and a Stanford professor. McCarthy developed one of the first programming languages called Lisp in the 1950s, and it is recognized for having an early proponent of the idea that computer services should be provided as utility. He was one of the first people, like in those days, back in the 1950s or 60s, having a personal computer was something almost science fiction. So what they did was they had these huge computers and they distributed that resources or time of the computer for anyone who wanted to use them. Just like it's done nowadays with TPUs or GPUs. McCarthy worked with Marvin Minsky, the third person on the screen here, at MIT in the late 1950s and early 1960s. And they together founded what has now come to be known as the MIT Computer Science and AI Laboratory, or CSAIL. Minsky was a leading theorist and cognitive scientist. He put forward a range of ideas and theories to explain how language, memory, and consciousness work. The core of Minsky's theory was called the Society of Mind, and he interestingly wrote something which I find very interesting. Uh, what magical trick makes us intelligent? The trick is that there is no trick. The power of intelligence stems from our vast diversity, not from any single perfect principle. The fourth person on the screen is Ray Kurzweil and has been a leading theoretician of AI since the 1980s. He has been working on optical character recognition and music synthesizers. Now, the reason why I even mentioned this is we'll go back to the previous slide once, and we'll see the last point on the screen, something that leads to the AI effect. So what is the AI effect? See, when in the 1998, this LeanNet came out, what LeanNet did, it was a neural network. It's still used nowadays. The latest version is LeanNet 5. But back in those days, once again, there was a huge lack of computational resources or GPU power. So LeanNet took on the problem of optical character recognition on vehicle plates. So for example, nowadays we have these cameras which will read your license plate number, right? So similarly, a similar problem was detecting which post code or postal code is there on a particular letter, so that post offices can quickly sort out where those letters have to go. So that was the problem decided by LeanNet. But nowadays, optical character recognition has become so easy and so simple that many people do not even call it AI anymore. It has become expected that any human or any machine can easily do this. So that is what the term AI effect means here. Now we'll interestingly go on to what the Turing test was about. So why is Alan Turing called the father of theoretical computer science? Because he designed a lot of the early uh, foundational stones of what we are going towards, or he had this vision of understanding what particular steps we need to take. So one of his greatest milestones was probably the Turing test. It was designed by him in 1950, and the Turing test is pretty simple to say. Imagine that there is a human interrogator, and in two separate rooms, in one room there is a computer, and in another room there is a human respondent. The only means of communication between the interrogator and these two entities, the human and the machine, would be a keyboard and the screen, so that language barriers and tone of voice did not create an impact on understanding who the human is. The game is about the human interrogator has to easily understand who is the computer and who is the human. Now, this does seem to be a very simple task, but interestingly, what happened was uh, the computer can ask any number of questions. I'm sorry, the computer can answer in any way. The interrogator can ask any questions as long as you can type it, and the computer can say they can the computer can give the truthful answer, or it can intentionally lie as well. The thing here is again dependent on what sort of questions is being asked. For example, the interrogator can ask the computer like, "Are you a machine?" So the computer would say no. The interrogator can then ask the computer to multiply to very large numbers, say 10-digit numbers. The computer can wait for a while and then give a plausible wrong answer. Again, the interrogator might be confused by this. Till date, no machine has been able to crack the Turing test, although we have reached levels, human levels, or even surpass human levels on a lot of smaller machine learning tasks. It could be object recognition, it could be detecting speech, it could be natural language translation. For example, no human can actually translate between, say, over 20, 25 languages, but Google Translate can do that for almost all the languages we know out there. So moving on. The reason I even discuss the Turing test is because reaching this is actually the goal that we as computer scientists or practitioners of AI or researchers in AI actually have. For example, one of my past projects was on tic-tac-toe, and I tried to beat this Turing test just for the game of tic-tac-toe, so that any player playing this game would not be able to differentiate if he is playing a human or playing a robot. And I feel that I have cracked this Turing test for this particular game of tic-tac-toe. But again, the Turing test was not designed for such small subtasks. It's meant to distinguish between a man and a machine. So introduction to machine learning. So what is machine learning? The thing which is written in red on my screen, pattern matching, that is basically all that machine learning is. It takes in some input data and it gives some results. So for machine learning, the more data you have, the easier it becomes for the machine to match the patterns in the data. And even till I think till 2017, and even now, a lot of researchers believe that machines actually understand what is happening or what tasks they have. But interestingly, a paper came out in 2016, I think. It was the best paper for ICLR, and it showed that machines can actually learn seemingly random noise as well, given there is a certain pattern in it, which human beings won't be able to know. I'll be giving a link to the paper in the next part of the workshop, but now let's move on. So we see that machine learning is a part of AI. Similarly, there we have expert systems, human-computer interfaces, etc., etc. A lot of different AI applications which are not machine learning. And what is deep learning? It's just, for example, in machine learning, we have neural networks, and in deep learning, those neural networks are just deep. There are certain points by which people try to distinguish between machine learning and deep learning by saying that deep learning actually finds more patterns, machine learning uses statistical means. I do not remotely agree to any of those points. Deep learning is just a subfield of machine learning in which we are using more resources, which traditional machine learning architectures like, for example, LeanIt did not have. And machine learning is when big data, algorithms, and technology comes together. A lot of data, smart algorithms, newer algorithms like whatever we'll be using, and technology. Right now, I do not actually want to go into the algorithms because it's an introductory session. So we have another fun video on screen describing what exactly machine learning is. Let's look at that.
Our ability to learn and get better at tasks through experience is part of being human. When we're born, we know almost nothing and can do almost nothing for ourselves. But soon, we're learning and becoming more capable every day. But did you know that computers can do the same? Machine learning brings together statistics and computer science to enable computers to learn how to do a given task without being programmed to do so. Just as your brain uses experience to improve at a task, so can computers. Say you need a computer that can tell the difference between a picture of a dog and a picture of a cat. You could begin by feeding it images and telling it, this one's a dog, that one's a cat. A computer programmed to learn will seek statistical patterns within the data that will enable it to recognise a cat or a dog in the future. It might figure out on its own that cats have shorter noses and that dogs come in a larger variety of sizes, and then represent that information numerically, organising it in space. But, crucially, it's the computer, not the programmer, that identifies those patterns and establishes the algorithm by which future data will be sorted. One example of a simple yet highly effective algorithm is to find the optimal line separating cats from dogs. When the computer sees a new picture, it checks which side of the line it falls on and then says either cat or dog. But of course there can be mistakes. The more data the computer receives, the more finely tuned its algorithm becomes, and the more accurate it can be in its predictions. Machine learning is already widely applied. It's the technology behind facial recognition, text and speech recognition, spam filters on your inbox, online shopping or viewing recommendations, credit card fraud detection, and so much more. At the University of Oxford, machine learning researchers are combining statistics and computer science to build algorithms that can solve more complex problems more efficiently, using less computing power. From medical diagnoses to social media, the potential of machine learning to transform our world is truly mind-blowing. To find out more about machine learning, visit oxfordsparks.ox.ac.uk, follow us on Twitter and find us on Facebook.
So that was a brief and fun demonstration of what machine learning is. Now we have a game here called Quick Draw. And the reason I want you to play this game is because it will give you a real example of where and how machine learning can be deployed. Please go to this link, g.co/quickdraw on your mobile phones. I'll also do it on my screen. And then I'll ask all of you, like, how can we design this game? Please don't judge my drawing skills here. I don't really know how to draw this. Please play this game on your own devices. The link is g.co/quickdraw. I would type it in the chat section as well. I'm pretty sure I can draw a balloon. Not bad. Yes. Well, this does not really look like a submarine. So I hope all of you actually understood, like, as we are drawing even, the machine would try to make some predictions underneath. So as I try to draw a toaster here, you can see that it recognizes it as a square, then as a dishwasher, a cooler, a purse, etc. So I would like to take a poll. Like, how many of you like can tell me like how this game was designed? Like, how does it work? We already discussed this. Like, it looks at some data. So I just want to hear it rephrased from all of you. Can any of you, like Vedant, Mahrukh, Shagnik, any of you just please go ahead, try to answer this? How does the quick draw game recognize what you're drawing as you're drawing it? It's really simple. It just looks at some data. That's it. So as we move to the next slide, we have like how is it recognizing your drawings and how could we program this? Well, Google created this data set. You can check out the data set as well at g.co/quickdrawdata. So there are about, let's see how many images are there. So we have 50 million drawings by people. So whenever I ask this question in workshops, often people come up with, it also stores whatever you are drawing. The reason Google actually does not do that is because it leads to a security condition in which people could draw something else and it could be misrepresented in their training data. Because machine learning, all it does is it looks at your data and it tries to match some patterns. For example, elbows have this right angle here, for example, on this arm on screen, or markers. Okay, this is asparagus. Okay, all right. So it finds these patterns. Now, what happens is, for example, it recently happened, I think in 2017 to 2018, when Trump was first elected. Uh, some people on Reddit posted a lot of content in which the word idiot appeared a lot of times. And uh, whenever someone searched Google for idiot, Trump's photo showed up. So that led to a massacre in which a lot of people were asking if the machine learning algorithm is biased in some way, but it's not. It's that game is actually called Reddit Gaming or Reddit Bombay. So whenever you give human beings the power to mess up with your data would get messed up, because even it might not be with a bad intent. Sometimes people just cannot draw very well. For example, I could not draw a submarine that well. So that's the reason Google actually has trained artists or normal people who are drawing them carefully, draw these figures, and these are actually checked before these are fed into the machine learning algorithm. So now we come to the question, like we have a lot of data, we have all these figures up here, but how do you understand if it's a tomato or what object it is? One easy task would be to write rules for all of them. For example, if you want to identify if a figure is a circle or not, or distinguish between a circle and a square, you should not be using machine learning. You should just see if the pixels on the screen or in the figure match a certain shape that you have or form the equation of a circle. For example, we know that the equation of a circle is x squared plus y squared is equal to r squared, where r is the radius. So that is something which a computer can easily do based on a certain rule. But as our figures become more and more complex, for example, in a carrot, you could first of all draw a cone, but then someone might identify it as an ice cream cone. Then you add some green leaves at the top. Then it still could be identified as some form or some flavor of ice cream. Then you add another rule that the thing at the top is not hemispherical in shape. In this way, we go on adding rules and rules, and for each object, if you have to add like 20 or 30 rules, and for complicated objects, if you had to add like hundreds of rules, then it becomes very difficult to maintain. So whenever another, say, developer is coming on the team, or say that this current developer who actually designed the system is not a part of the company for any reason, in that case, managing this huge code base would be very difficult. So, what are the techniques which we can use here? The other approach would be using machine learning. So we can show the machine a lot of images of carrots and tell it to learn some features. So what do features mean? Features are simple edges, corners, gradients, colors, or we'll actually be seeing what features are and what higher order and lower order features are. For example, the features which I just mentioned, like edges and corners, are called low order features. These would be determined. These would the machine would learn them in the very first or the first few layers of the neural network. As we go deeper, the machine would start learning more deeper features. For example, whenever you or a human being is looking to identify the face of a person, what features do they look for? People look for features like eyes, nose, ears. When we identify all of them in the places where we expect them to find, that it identifies them as a face. All right, so Haven, it keeps learning as we draw. Yeah, that is partially right. I think I did not see your reply at the moment. So yeah, it does learn as we draw, but it does not do on device learning. So for example, if I draw something wrong, quick draw won't actually be affected, and it finds the similar and the most closest object. Yeah, that's absolutely true, Shubhu. What is being done is whenever you are drawing something, at every iteration or at every second, it would note down or extract the features and find out in its database, say it has 100 pictures or 10,000 pictures, it will find which object in the database is the closest match or has the most number of features similar to the features which have been extracted from our image. So for example, in this carrot, we can extract the feature of a cone, we can extract some jagged edges at the top where the leaves of the carrot are, and it will try to match it as such. So this is an object detection problem. could also be object classification, like say you give an object and it identifies it as a carrot or a cat or something. This is classification. Now, if it has to draw a bounding box, like where this object is, that problem is called object detection. But enough of that. Let's move on to this understanding. Like we already spoke about rule-based and machine learning, the two approaches by which we can identify a certain object. So when should we follow any of these techniques? And I really want you guys to answer this question. So which approach do you think is best if you need to alphabetize a list of song titles? See, I have some songs like Stairway to Heaven and Demons. Two songs which I have. Should I be using a rule-based approach or should I be using machine learning for this? Uh, no, yeah. Arvind, even if you have a very large data set, whenever you have a very large data set, usually a machine learning algorithm is the best or the preferred way of approaching the problem. But for something which is just a sorting, alphabetizing a list of song titles, this can be done by simple sorting. So even if you have a lot of data and the time taken for a machine to make sense from that data would be huge. It would be more efficient if you can use a rule-based approach. And in fact, using a rule-based approach is always the better idea if you have simple rules which can be extracted. Say, for example, for the object classification or detection problems, we do not have simple rules which can be extracted. But for simple alphabetizing, in say for example, forget song titles. Consider a simpler problem: arranging a list of words in the dictionary order. So that would, alright, yeah, alright. I'm sorry for misunderstanding you then. Yeah. So what I was talking about is, uh, if you have a small list of titles, it's or a large list of titles. In this case, the correct approach would be rule-based. But in my next question, you will find some questions in which using a machine learning algorithm would be better, or maybe even using both. So let's look at the next question. Ranking web search results. And good job, Maruk, Arvind, and Amarish for actually finding the correct answer. So what do you think for ranking web search results? Which approach should be used? Okay, so we have one answer for machine learning from Amarish. Arvind. All right, anyone who thinks the rule-based approach would be better? Machine learning is definitely an idea here when you're ranking web search results. Yeah, Amaru, could you turn on your mic and let us know how rule-based approaches could be better? Or write in the chat section, whichever. I think turning on your mic would be faster. All right. So, see, if you have a lot of data, yeah, machine learning is definitely a good way to. But sometimes, or even till 2014, most of Google's search results had some rule-based approaches. Rules were hard-coded into those algorithms. For example, say I'm from West Bengal, and we have a band called Fossils. So when I'm searching for fossils, I always see information about the band, their music, etc. I would not be interested to look at dead people. But on the other hand, someone who's a doctor and often searches for bones and stuff doctors search for, which I would not be very well aware of. So that person would definitely be very interested in actually knowing more about fossils, right? Or archaeologists for that matter. Another example is, which I actually read from Google's implementation on this, was between the Boston Giants and the LA Giants. So in America, these soccer teams are called giants. So someone from that uh, geographical location, whenever they search for giants, they're probably, if they're in Boston, they're searching for the game times for Boston Giants. Whereas, say, someone from Australia, they would definitely not be looking for information on Boston Giants. So when they're searching for giants, they're probably looking for big people. So initially, Google did have a lot of rules, and now those rules have been reduced because they collected a lot of data. I think the correct answer here is both of them. So I hope that this answer was a bit eye-opening for all of you. So we always try to develop rule-based approaches, and we go for machine learning only when we have enough data. Again, predicting house prices based on location. What do you think would be the answer for this? All right, we have machine learning from Ramansh, Vedant. Anyone who thinks it's rule-based? Well, like the previous example, it could be a rule-based if we do not have enough data, but usually we do have a lot of house price data, because even before machine learning came into existence, people have been selling houses, and they have been keeping the records of where the house was, how big it was, the length of the house, the breadth of the house, etc., etc. But again, these features might not work very well if there are rules like if it's sea facing or not, if it's in the center of the city or not. So some rule-based advantages are also there. But again, if you have really a lot of data from similar houses nearby, then machine learning would be a better choice in this case. I think the correct answer would be only machine learning here. Again, processing online payments. This interesting one. So is it rule-based or machine learning? I really like it that you all are interacting with this with me and answering the questions. So for processing online payments, what do you think is the correct way to go? Can it be done with simple rules like checks and balances? Yes, indeed, it is rule-based. Three people have answered: Vedant, Mahrukh, and Amarish. You are right. It is completely rule-based. But recently, you might have seen it whenever you try to transfer some money with Google Pay, they tell you to turn on your location. So they are using some machine learning there, but that's for the security of your application, not exactly for the online payment. So once you are verified that you are indeed the person you claim to be and that you are the person who is making the transaction, then the rest of the transaction is completely rule-based, just server-side verifications, etc. Classifying an object in a photo. Well, this is something we have been discussing a long time for. So yeah, that's machine learning. Because there are n number of objects in the universe, and we cannot possibly write rules for every single object. So if you're trying to say classify or say distinguish between your monitor screen and a football, then again I would be using a rule-based approach every time, not machine learning. But for in general purposes, it's always better to be using machine learning. Again, you might be asking why I chose this example, a monitor screen versus a football, and I said machine learning. Why is it rule based when machine learning could do the job? The reason is that see, a monitor screen would always be rectangular, features which can be found very easily or detected using classical image processing techniques, and a football is almost circular, although it has some background which can be easily removed from the image. So that's the reason why a rule-based approach could work for, say, distinguishing between two objects which are very much dissimilar. Ah, I see. Curved monitors aren't rectangular, but even in that case, like yeah, you're right in one scenario. Like whenever I speak of monitors, I always talk about the monitor from the exact front point of view, etc. So for example, if you have the monitor from some side view or from the top where it would look like a curve, in that case, yeah, using machine learning would definitely. Okay, yeah. That's a fun question. What if the monitor has footballs on it? So you mean like there are footballs on your screen? Yeah, yeah, that's a really good question. And even like in that case, a good algorithm would find out both of the objects and draw bounding boxes. A bad algorithm would just give a random result. It would be confused. So yeah, and machine learning algorithms are also much more robust to noise, angle, uh, etc. So yeah, this was a useful discussion. Now let's move on to the next point here, which is let's just look at the pros and cons of both of these techniques. So for rule-based, we have to define the rules, and improvements come from newer rules and uh, designing a better network, etc. Machine learning is much more simpler to manage in the long run. You just feed it more data, and improvements can come from additional data. Each of them has its pros and cons. So idea to implementation. So we won't be actually dealing with the process of how a machine learning pipeline works in detail, but we will be looking at a brief overview. So whenever people talk about machine learning, they always think that you have some problem and you solve it. And the problem is something like uh, finding faces in a picture, or finding if how many people are dying in the Titanic problem, like the popular problem on Kaggle. But that's not how real world machine learning looks like. So whenever we say we go to a startup or we go to a company and we're trying to solve a problem, it's always a business problem. And our primary goal is making profits for the business. So how do we make profits for the business? Now we are moving on to this interface between managers and data scientists. So now we have to actually define a clear mathematical objective in which the goal can be achieved, like some loss function can be maximized or minimized. We will be discussing what loss function is here, but for now, let's just say that we have a clear objective, like how do you understand that the number of faces we're detecting is very good? So, for example, we could have a percentage like number of faces in the image, the real number of faces versus the number of faces our algorithm has detected. Something that can be mathematically put down. That's the objective. After that, we collect some data, we train and test some model. Already, machine learners have some idea about what sort of training and testing uh, to be is to be done, what sort of models to use. But even then, it's still a lot of trial and error is there. Even for our problems, we often end up choosing 2 or 3 separate algorithms. And even after realizing that okay, this is the algorithm which we need to use, we often try different architectures with more neurons, less neurons, more layers, etc. So that's the stage where which what is called predict and evaluate, and then we either go back to collecting more data if everything's going on well, or if we see that we are achieving our goals but our customer is not satisfied, then we go back to understanding the customer again, like why are they not satisfied? Has there been some mistake, or have we missed some crucial objective in our machine learning process? So whenever we talk about machine learning, we have to make sure that there is no bias or that the machine learning algorithm is very robust. So how do we do that? Let's see that in this video.
Let's play a game. Close your eyes and picture a shoe. Okay, did anyone picture this? This? How about this? We may not even know why, but each of us is biased toward one shoe over the others. Now imagine that you're trying to teach a computer to recognize a shoe. You may end up exposing it to your own bias. That's how bias happens in machine learning. But first, what is machine learning? Well, it's used in a lot of technology we use today. Machine learning helps us get from place to place, gives us suggestions, translates stuff, even understands what you say to it. How does it work? With traditional programming, people hand code the solution to a problem, step by step. With machine learning, Computers learn the solution by finding patterns in data. So it's easy to think there's no human bias in that. But just because something is based on data doesn't automatically make it neutral. Even with good intentions, it's impossible to separate ourselves from our own human biases. So our human biases become part of the technology we create in many different ways. There's interaction bias, like this recent game, where people were asked to draw shoes for the computer. Most people drew ones like this. So as more people interacted with the game, the computer didn't even recognize these. Latent bias. For example, if you were training a computer on what a physicist looks like, and you're using pictures of past physicists, your algorithm will end up with a latent bias, skewing towards men. And selection bias. Say you're training a model to recognize faces. Whether you grab images from the internet or your own photo library, are you making sure to select photos that represent everyone? Since some of our most advanced products use machine learning, we've been working to prevent that technology from perpetuating negative human bias. From tackling offensive or clearly misleading information from appearing at the top of your search results page, to adding a feedback tool on the search bar so people can flag hateful or inappropriate autocomplete suggestions. It's a complex issue and there's no magic bullet, but it starts with all of us being aware of it so we can all be part of the conversation. Because technology should work for everyone.
All right. Uh, so this was actually one of the most important videos in this workshop. Now we discussed about what interaction bias, latent bias, all these biases are. So let's see what can machine learning do. One of the tasks which machine learning can do is called classification. So we can have binary classification or we have multi-class or multi-label classification. So let's first of all think about what binary classification is. It very simply put, it just distinguishes between two classes. For example, it can be people who have cancer and people who do not have cancer. Very simple, clean differentiation. What multi-class would be is what sort of classification was being done in the quick draw game. So what was being done is whenever you draw an object, it can belong to multiple classes, like those patterns which have been extracted from your image. They can be put into multiple classes. For example, a notebook is also rectangular. Similarly, the top view of a box is also rectangular, and the sheet of paper is also rectangular. So it would be recognizing your the pattern which you have drawn or the figure which you have drawn as all of them. So that's an example of multi-class classification. Now, what is multi-label classification? When the same object belongs to a lot, multiple can be given multiple labels. For example, in this figure, we have drawn a lion, and it can be a lion, of course. But if you also have these labels like a lion, wildlife, boy, girl, mammal, truck, car, so it's also wildlife and it's also mammal. So I hope this this difference between multi-class and multi-label is clear for all of you. So to reiterate, multi-class is that you are finding out the multiple classes to which an object can belong, and not just two classes. So your targets, in your target, there are multiple classes. So an object can be A or B or C or D. And multi-label is when the same object can be multiple of those target values, not just one of them. So Another thing which machine learning can do is regression. Very simply put, regression is just drawing a best fit line. So you have some data points and you're drawing a best fit line. So whenever we used to draw a best fit line in school, what did we do? We just put the ruler, and with our eye we used to measure like, okay, so this is close to the values in our data set, so this is very good enough. Another more mathematical way of doing it would be to take the difference in y coordinates between two random points and divide them by the difference in x coordinates. So then you get the slope of your line. So you can put that in y is equal to mx plus c and get your line as well. So machine learning algorithms try to find these m, x, and your m and your c. So if you have a single perceptron layer neural network, okay, what it means is if you're just trying to simulate what linear regression does purely, a single neuron can do that. And we'll be seeing that in our live demo today. So regression, the difference between regression and classification is that regression would point to a continuous stream of data. That is, the output would be continuous. In classification, your output would not be continuous. It would be discrete, say a lion, a tiger, etc. And regression and classification problems can both be transformed from one to the other. For example, if you have a classification problem and you are, for example, classifying between people of ages 18 to 24, 24 to 30, 30 to 36, if you make those classes smaller and smaller and smaller, you could get almost a continuous set of values. For example, 18 to 24, you divide it into 18, 19, 20, 21, 20, 23, and 24. Okay, so your single classes now become 7 classes. Similarly, you could distribute your entire data set and retrain the neural network, and then it would look more like a a regression problem. Again, a regression problem can be transformed into a classification problem. How can you do that? So currently what you're doing is, say, a taxi cab fare prediction. So you just are predicting like your fare would be say 240 rupees or 250 rupees. But instead of giving the actual value, you can give the rider an estimate. Say your cab fare would be between 260 and 270, 270 and 280, 280 and 290. So that could also be a problem. And in that case, you have transformed your regression problem into a classification problem. Oftentimes, converting regression to classification has a lot of use cases. For example, you might not want to give your customer an exact trip estimate because, for example, if I give an estimate to the customer, like it costs you 292 rupees, and the actual fare turns out to be about 320 rupees. So the customer is paying more. He would be like, okay, you are overcharging me. But if I give the customer an estimate, say 290 to 320 rupees, and he's paying 320, then the customer would be happy. On the other hand, for classification to regression, I have not really found that many use cases, but maybe that's just because we do not have suitable data as well. But it's possible, both of the transformations are possible. Which algorithm we are using depends on what our end goal is and what sort of data we have. Another problem is clustering. So say we have a lot of handwritten digits. Some of you, if any of you ever heard of the MNIST data set, it is basically handwritten data points, say 1, 2, 3, 5. Thousands of people have just written these digits and these have been extracted. So now we have these handwritten digits, and what we can do is the machine does not actually know what 7 is or what 2 is. It will just look at the data and find whichever images have similar patterns and group them together. Alright, so we can expect that the 7s will be grouped closer to the 1s because some people's 7s look like 1s, some people's 9s look like 1s, so on and so forth. So one point often people ask is what's the difference between classification and clustering? Because in both of these problem statements, what we're doing is we're taking the data and we're putting them into certain classes. Well, in classification, we already have both the inputs and the outputs. It's a supervised learning problem. So, for example, if you want to classify a person as a Say we are classifying between cancerous cells and non-cancerous cells. So we already know what cancerous cells look like, and we have a lot of images of cancerous cells, and we have the label, yes, cancerous. And on the other hand, we have a lot of images of non-cancerous cells, and we have the label, non-cancerous. So the machine is learning this pattern, like whenever these patterns are there, it is cancerous, and whenever the other set of patterns is there, it's non-cancerous. But in this problem of clustering, we do not actually have any labels. We just have these handwritten digits. We give it to the algorithm. We do not have any number of classes as well. Like we do not know how many sort of digits we have. The machine has to find this out on their own. So that's clustering. And actually telling the machine how many of those clusters are there would make its work easier. And that's one of the hyperparameters which we have tuned. For example, say we do not know how many digits are there in the English language. So if we are trying to use a cluster size of 4 or 5, we'll get some value results. And if you're using a cluster size of say 100, we'll get some results. But those results won't be very good, because if you're using a cluster size of 100, even the sevens will get divided up. Like some people who put a cross in the vertical part of the 7, like put a horizontal line, cut off their sevens, that would be one cluster, and those who do not cut off their sevens would be another cluster. So I hope this makes sense. So this is the difference between classification and clustering. Now we have sequence prediction. So sequence prediction is often used in our keyboards, like whenever you start typing some word, it will predict what your next character could be, or the next word, or the word that you are trying to write, so that you do not actually have to move your finger through the entire sequence. Style transfer. This is an interesting problem. Many people think of style transfer as just like you have a painting or a figure, and you're trying to draw it in, say, Van Gogh style or Picasso style. But that is not actually the entire goal of style transfer. Style transfer is basically the transmission of information from one source to another, one entity to another, changing the mode of communication. For example, say some text is written in French, and that is being translated to Spanish. So the text, the information that the text is trying to express will remain the same, but the language of the expression would change. The language here, the human language, is changing. Similarly, another example would be, of course, images is there. We have given the example of normal languages. Another language could be just the tone of voice. For example, a boy who is talking, you could record a voice and transform that into a girl who is talking, because the voice, the pitch, the modulation, that would be different between a boy and a girl. So if you're doing that, that's also an example of style transfer. So here, what the image is not actually very clear, but you can understand it in this way. The EN male is trying to say something. The EN female's voice pattern has been on the screen in the second row, and the JP male is trying to say what the EN male is saying in the tone of the EN female. So that's also an example of style transfer. Do you have any questions, Dylan? Let's pause for a moment and see if anyone has any questions. Then we can proceed with the rest of the workshop. All right, let's proceed. So now we discuss the various types of machine learning which exist, like classification, clustering, regression, sequence prediction, style transfer. I want you all to tell me which algorithm you find would be suitable. And do know that there is no one correct answer. There can be multiple correct answers here, so feel free to go ahead. Like recommending what someone will download based on previous purchases. So what sort of algorithm can we use here? All right, clustering is definitely a good idea. It's definitely not going to be regression, because we do not have a continuous set of outputs on which we'll map our input data. So it's not regression. Classification, no, not really, because in classification, what we'll be doing is we'll Okay, one thing which you could do is classify buyer types. Like, okay, this person is a buyer who pays a lot of money, who buys a lot of stuff. Okay, that sort of classification can be done. Like buyer mentality classification can be done. But what object that buyer would buy, that cannot be called classification, because even if you know that I spend a lot of money, it does not mean every time I go to the market I'll buy a gold necklace or something. Or even if you know that I am not gonna spend a lot of money, it does not mean every time I'll be buying something cheap. So we have some other answers like clustering and sequence prediction. All right, so let's talk about clustering. This is useful. Clustering is actually used for this problem. Like someone who is buying a lot of cake ingredients which are required to make a cake, say flour, essence, etc. It's possible that they would be buying probably more ingredients to make a cake, or maybe candles and stuff. So that sort of clustering could be done. But again, there are some downfalls of both clustering and sequence prediction in this case. The downfall is that, say, yeah, this example was from a University of Washington course. I clearly remember. So the instructor was saying, like, say a group of customers has gone to the market, one, and they are similar. Like we know from previous analysis that these two customers are similar. So one of them goes on and buys a lot of baby products. That does not mean the other person would also be buying baby products. Also, another point here would be. Just because a person has bought a lot of baby products today does not mean they would buy baby products every day, because maybe they are just going to a baby shower, or some of their friend had a baby to whose place they visited. Alright, so classification. Maruf has a point here. He says that like boys, girls, toddlers, clothes, shoes, makeup, facing classes. Uh, no, actually, what the question here says is that say you are distinguishing between boys and girls, or yeah, so market classification, the example which I gave. Now the thing here why classification does not exactly answer this question is because even if you know that your customer is a guy who is a teenager, it does not mean that every time they go to the market they would be interested in the same sort of products. For example, say you are looking at a lot of laptop skins today. Like just today I actually bought a laptop skin, so I have been searching the internet for the past 2 days for laptop skins. Okay, that does not really give you a good idea about what I'll be buying next. Sequence prediction is actually a good idea, like, but it does not always work. Clustering is also a good idea. Let's see what the correct answer here. So the correct answer here is sequence prediction, but nonetheless, clustering is also a possible explanation in this case. Labeling email as spam or not spam. Uh, this is okay. I won't say anything right now. Please try to answer this. For example, I can give you a hint, like it's definitely not going to be style transfer or sequence prediction. So that's out of question. Classification, okay, classification. Well, okay, yeah. So if you have two classes, spam and not spam, you want to classify an email, that's clear cut only classification. But if you want to give the user a confidence metric, say in which it's written like, okay, this is 25% chance that this is spam and 30 and 75% chance that it's not spam, then that would be a regression problem. So again, one problem can be both classification and regression, but definitely here the answer would be only classification. Determining workout activity based on phone movement. Okay, we have a question. What about clustering? See, clustering won't be an option here because whenever we collected our data, we already had the labels that this is spam and this is not spam. Clustering is actually used for labeling in spam versus not spam as well if we do not have the labels. So yeah, it could be an option, but usually whenever you're training, there's also something called semi-supervised learning besides supervised and unsupervised. So in that we actually add some labels ourselves. So for example, we have a lot of emails in which we do not know if it's spam or not spam. So we'll have some human beings actually label them like, okay, this is spam and this is not spam. The reason you always try to prefer using a supervised algorithm is because they will give you a better accuracy, and they are usually faster to train as well because the machine is not scrambling around looking at things it does not understand or patterns it cannot understand. All right, so we do not use clustering usually for this problem. The answer would be classification. So the next problem, determining workout activity based on phone movement. So is that classification, clustering, or regression? Again, it's not sequence prediction or style transfer. No, I just said that it cannot be sequence prediction or style transfer. But let me point it out. Like, see, the reason it cannot be sequence prediction is it's not very easy for a machine just from phone movement to understand what the next sequence would be. For example, how would I put this? See, usually when we talk about sequence prediction, we clearly know like these buttons have been pressed or this action has been done. But from phone movement, what they're trying to point out is, I'm sorry, okay, you already saw the answer, I guess. But anyway, we'll still discuss why that was the answer. The reason it's not sequence prediction is because we do not have a clear set of actions which is being done. Say, what sort of data can you get from phone movement, like the accelerometer, the gyroscope, etc. So you can understand that this person is jogging, or this person is doing a bench press, or this person is running a marathon, something like this. Now, if that is our goal, like distinguishing between bench presses, push-ups, pull-ups, and marathon, we have clear-cut classes, and it would be a classification problem. Done and dusted. Now, if we're trying to say from the phone movement, trying to understand if the person is running a marathon or running a sprint or say just jogging, this is more of like we could say the speed the person is moving with. That would be an effect of the workout activity or a feature of the workout activity, and that could be a regression problem, like the speed with which the person is moving. Some features which you can get from the phone here is that like the person's heartbeat or any data which you can get from Samsung Fit, etc. So in that case, it would be a regression problem. If you try to say like this person is doing 50 push-ups per minute, okay, that's too much. So like 20 push-ups per minute or something like that. In that case, it would be a regression problem. But in this particular case, as we already saw, the answer is classification because it's just distinguishing what particular activity you are doing. Also, there was one answer for, okay, we already discussed regression, we discussed style transfer. Okay, we did not discuss style transfer. Why do you think it would be style transfer? There is see the movement which you get from the phone is just accelerometer readings, gyroscope readings, etc. So there is no information in these patterns as such. So there is not exactly enough information to transfer, and style transfer is not one. Is my explanation enough? Like I don't think I could explain it well enough. Uh, so your phone has these sensors, and they are having some. They're giving some values. See, when we talk about style transfer, you already have an image or have a sentence or have a complete human understandable information. So that is not there in this case where you're getting the data from phone movement. That's the reason it's not style transfer. So we're just trying to read those inputs, which is like accelerometer, gyroscope, your heartbeat, etc. And we're trying to classify which exact activity is happening right now. So identifying famous landmarks in a photo, that's very simple. It's a object detection or a classification problem, something like that. Estimating arrival time based on time of the day and traffic is a regression problem because we already know that these are the features there at the intersection, and this is the time it takes for a certain vehicle, be it a truck or a lorry or a bus, to the estimated arrival times or wait times at a particular intersection. So since your output here is continuous, like it could be 10 seconds, it could be 15 seconds, or it could be 10.2 seconds, that's why it's a regression problem. It definitely cannot be a classification or any of the other options. Translating within two languages. We already discussed this translation thing very clearly in style transfer. Alright, so let's watch a short video on neural networks, and then we will actually just jump into our actual hands-on labs as well. This is a pretty good video. I hope the audio is it's
Hi, I'm
perfect.
Nat. And I'm Lo. And this is our 20% project, where we go find out about different Google stuff we're curious about.
Last year, we got to make a documentary about how voice search works. And that was the first time we heard about something called machine learning.
Since then, we've been kind of fascinated by it.
So today, we're talking with Greg and Chris to learn more about it. How would you describe machine learning to someone?
Well, there's a lot of problems that's really easy to solve with computers. Computers can go and simulate how galaxies move and how the courses of asteroids going and how close they're going to come to Earth. I could never hope to go and do that, but I can go and do this problem like recognizing that that's a tree, which is so much tremendously more difficult for a computer.
It doesn't feel like intelligence to us because it's so effortless as a human being to do it. But for a computer, it's actually really hard.
Because the real world is kind of messy and unpredictable at times. The strict logical rules that go into traditional programming just don't work.
Instead of going and writing programs that solve the problem, we write programs that learn to solve the problem from examples.
And it's this process of learning that allows them to improve over time and to actually be more clever than they would be if we wrote down a very rigid set of instructions for them to follow.
Machine learning is in so many different things that we use today that it's kind of like this invisible magic ingredient.
Phones with the ability to understand human speech.
Machine translation, email spam filters.
When you go to the ATM and you give a check and it can read the handwriting.
Or a Photos app that can automatically organize your photos based on the things that you like to take photos of. Like, here are all my mountain photos, here are all my food photos.
Here are all my dog photos.
Here are all my feet photos.
Everything from facial recognition to going and trying to recognize whether a particle is present in a particular collision at the LHC.
Which we would just like to take a time out to say is that big tube in the ground over in Europe that smashes particles together at really fast speeds so that scientists can use that information to unlock the mysteries of the universe, among other cool things. Now back to our episode, because I am getting really dizzy doing this. Ooh, ooh.
So researchers and scientists are still experimenting and trying to find the best ways to teach computers how to learn. But a lot of the progress is coming from these algorithms that are based roughly on how the human brain works, and these are called artificial neural networks.
So an artificial neural network is something that it's a rough mathematical cartoon of how a biological neural network works. In a biological brain, we have individual cells called neurons. Each neuron looks at what its neighbors has to say and then decide what it wants to say. And in artificial neural networks, we have little mathematical functions. We put them in some organized structure, and then we say, okay, you guys all together, learn to do this task.
We have lots of neural nets that are really great at going and recognizing, this is a cat, this is a dog, this is a frog, this is a mouse, this is a horse, this is a truck, and things like that.
So take, for example, trying to recognize what this is.
So it used to be that we were really proud if we could get a neural net with 3 layers to work. And it's recently that we've made a lot of progress on techniques that allow us to train much deeper neural nets.
And that's why this kind of machine learning is also called deep learning. A neuron in the bottom layer is just going to be looking at a tiny piece of the picture and making some computations about it. It doesn't understand anything about dogs specifically.
But what the neuron does understand is it says, I'm giving a signal that's useful for somebody who's giving a signal, who's giving a signal, who's giving a signal, who's giving a signal.
They're kind of able to unfurl this really high-dimensional knot and pull it apart and make it easier to go and you know, separate different things that are close together on the surface from things that were tangled all together earlier.
But then at the top, we'll put 2 neurons, and these neurons look at the whole picture so far.
They're basically experts at making the final call, figuring out, oh, all the layers below me said these things, so I know that this is a dog, or at least I'm 92.4% sure that it's a dog, so it's basically a dog.
And while there's been a whole lot of progress with teaching computers to learn, they're still much slower learners than we are, and they make mistakes that you and I wouldn't.
So what I was working on is sort of trying to find a way to go and look at a neural net and ask, what does the neural net think the platonic ideal of a cat is, or the platonic ideal of a dog, or anything it can classify as? And suddenly you can go and ask, you know, neural net, what do you think a cat looks like? And you get a picture of a cat. Or, you know, neural net, what do you think a barbell looks like? So these weights. And it goes and it shows you a picture not only of a barbell, but of an arm attached to a barbell. So the model thought that the arms, you know, it only learned what barbells were from looking at pictures of barbells, and they're often held by muscular weightlifters. And so it learned that there was, you know, barbells have arms attached to them.
It takes them a long time to learn. If you show it a picture of a school bus, when it's early in learning, the very next time you show it a picture of a school bus, it's only a little bit more likely to say school bus. It doesn't get it, even though that was the very last thing it saw. Whereas, you know, you say to a kid, you know, that's a filing cabinet. And then a second later you say, what's that? Yeah. He's not gonna be like, shoe, right? You know.
Well, like, the more you describe this, the more I'm amazed by human beings.
Yeah.
Like,
yeah.
The effect is like, wow, human beings are really amazing.
We're really amazing learning machines.
Oh. Alright, so I hope you enjoyed the video. It actually talks about some of the differences between human intelligence and machine intelligence. And actually, when I first had seen the video, I came to the conclusion that human beings always look at the higher order features first and then at the lower order features. This stemmed from my understanding of machine learning at that time, and also neurons in the brain working. Like, what I used to think was that human beings always look at the higher order features first. The reason why I thought this is because we can easily distinguish between a water bottle and a computer. But again, we have to distinguish between a water bottle which imagine this water bottle which is thin, which is completely dark and cylindrical. That sort of a water bottle would also look like a perfume bottle, right? So that sort of recognition is sometimes difficult for humans as well. So this led me to think that humans only look at the higher order features first, and then with more and more practice, we learn to distinguish between objects which are similar but not exactly the same. For example, different types of water bottles, different types of perfume bottles. All perfume bottles look the same, but they have brands which are mentioned in the bottle names. But well, that was not actually right. Later I got to know that humans also actually look at the lower order features first, and the mind very quickly computes the higher order features. And with more, the reason we actually get better as we look at more data is similar to machines. If you feed machines more data, they will get smarter. So actually the way human beings think and the way machines think is, or at least from the machine learning that we know right now, they are massively similar. So in this figure we see that we're trying to distinguish between a cat and a dog, and it's trying to recognize the features that are there in the cat, and it's some of those neurons are getting turned on, and those are propagating to the next layer of neurons, and that's getting propagated to the next layer of neurons, and it's getting it that it's a cat. So what happens here is that we initialize these weights. So each of these layers which you see in this figure is a layer of a neural network. We take these neurons, we initialize them with random weights, and we already give it the output, like this is a cat. So if it does not get the correct answer, it knows that it has made a mistake, and so it tries to move back in the neural network, updating its weights, so that it will keep doing this process as long as you run the algorithm, but as long as it tries to reach the it tries to simulate or get closer and better patterns in the neurons as well. So, alright, to give you a bit more clarity on this, let's look at this figure here. Alright, so we have a picture here which has a dog and a cat, and we see that in the initial layers it's looking at small parts of the image, and it's trying to find out, okay, so this is what a dog's head looks like, okay, so this is what the face looks like. This is actually a very simple representation. It won't be this smaller neural network would never be able to classify between a dog and a cat. But anyway, so we see that the lower order features are detected first and the higher order features are detected later. So in the last layer at the top we have a complete dog's face. So if that is there, this is definitely a dog. And here they are actually trying to find out the breed of the cat and dog as well. So each of these pictures which you see in the neural network, these are called feature maps. So each of these are called feature maps, and these are something which the neural network will learn on its own through training. So what sort of training can we do? Now, to discuss this, we could directly jump into a hands-on lab with neural networks. But first, let us go back and try to see what linear regression looks like. And then we'll see how we can compute a linear regression using a single neuron much quickly and much easily from a code perspective as well. Alright, I assume that many of you here would be knowing TensorFlow, Python, etc., but I would not be making this assumption. I would be explaining the code line by line. So if any of you have any questions, feel free to put it in the chat section or feel free to turn on your mic as I'm explaining already. Do not feel shy in this. Alright, so firstly, the example which I have here is of by the way, do you have any sort of interference? Like it has started, the storm has started here, and can all of you hear my voice clearly? If you can hear my voice clearly, just type in yes. All right, okay, so it's audible. Sometimes when these storms start, the voice gets very shaky, etc. Anyway, so we are using a Python 2 and TensorFlow version 1.15, the previous version of TensorFlow for the first example. Actually, I have used import TensorFlow that compared v1 as TensorFlow. The reason I had to do this is because although I'm using TensorFlow 1.15, TensorFlow on Google Colab does not support it anymore. So if you want to use TensorFlow 1.15, you have to write those two lines. Alright, we have imported the normal libraries NumPy for numerical computation and Matplotlib for plotting. Now what we have done is we have generated the dataset, and this is the dataset we'll be using throughout our linear regression demonstration. So we are creating some x's and some y's. The x's have to map to the y's. So x is 100 values we are generating between 0 and 2, which are equally spaced. This code, which is highlighted here, generates 100 values equally spaced between 0 and 2, including both of the values. And we are generating the y as 1.5x plus 0.5 plus some random noise which can be at most 0.2. So for example, if your x is say 1, alright, your y should be 1.5 plus 0.5, that is 2, plus some random noise, some random additive noise. Alright, so we are generating 100 values. We are creating 100 x's and 100 y's. We just created a function. We did not actually create the values. Let's call the function, and we can print the x's and the y's as well. Alright, so here you see that we have generated 100 values of x in the first set here. These are the x values because I wrote print x batch. And next we have 100 values of y here. Yeah. All right. So now let's plot these values in a graph. Alright, so this is what our data distribution looks like. Because we added that random noise, it won't be a straight line. And this is why it will be a little difficult for a neural network to learn. But I think, I'm sorry, a linear regression model to learn. But I'm pretty sure it will still do this. So when we are making a linear regression model, what is our goal? Our goal is to reduce the loss, which is the distance between the x's and the y's. I'll go back to my slide here. All right, so as you see that these points are there, and this is the line which is being predicted, the blue line, and the loss is actually the difference between the blue point and the intercept it cuts on the line which has been drawn. So for any particular x, there would be one y which is the actual ground truth value and one y which is the predicted value. So we are trying to minimize the sum of the squares of those differences. And why sum of the squares? It could just be sum of the differences, right? The reason is that say your ground truth values are 0, 1 and 2 and you are predicting 1 for all the values. Now if you did not take squares, you would actually get 1 minus 1 and 1 plus 1 as your error. And when you sum them up, what's your output? You get 0 as your output. So your neural network, your linear regression would think like it has got a perfect fit, while it would not actually be correct at all. So, Mahrukh, you said that is this a matrix? So are you talking about this thing here? Are you talking about okay, yeah, exactly. Okay, so those are not matrices. Those are just call them lists. Imagine you have one row which has 100 values and another row which has 100 values. You can call it a matrix, but we are not using this as a matrix here. All right, those are just two lists of 100 values here, 100 values there. So given this x value, yeah, exactly, it's an array. So given this x value, it has to point to that y value. All right. So we have plotted these values here, and what we want is we want to, if the figure is here, yes, we want this. We want to draw this red line on the figure, which is the value of your linear regression. By the way, if any of you want to use this code or view this code after the workshop, this would be available on my GitHub on a repository called Explainable CV. I will share the link with you right now. All right, I have shared the link. So this is the point at which we have discussed. We have plotted we have created these points, x's and y's, and we have plotted them. Now we are coming to the meat of the algorithm, or the linear regression. You not exactly have to understand all the code here, but I will still go through it line by line. Basically, in the very next slide, we will be showing you how to skip over all this code and write this entire code in like 1 or 2 lines. So firstly, we are using a placeholder. This is how in TensorFlow 1, we had to define our variables. So this is x and the y, and the weights which are being updated as a result of this linear regression or the back propagation which will happen in this network. To move those weights across and to update them, we had to write something called with TF, the variable scope. But now in TensorFlow 2, there is no more variable scope as well. Anyway, so weights and biases are the values or the variables which will be changed at every single epoch or iteration. And at every epoch or iteration, what is the goal here? We are calculating the y prediction, which is w into x plus b. You could just write it as well, w into x plus b. That also works. And we are reducing the mean, which I just explained through the figure on my slide. we are trying to reduce the sum of the squares of y prediction minus y. So if your y prediction is the point where, let me go back to this slide once again. So as soon as you see this lines coming here, see where my mouse pointer is. This is the value of y predicted for this particular value of x, and this is the true value. So that's the y prediction, and the actual y value, the ground truth. You subtract them, find out the differences, and you square those values. And you take the sum of squares. This is what your loss function is. And you reduce the loss. That's your goal. And this is the linear regression code which you write. You can just run the function and then call the linear regression training as well. I'll start the training and explain line by line as it trains so that we can save on some time here. So here we have defined an optimizer called gradient descent optimizer. Gradient descent is a process by which your neural network would find the best weights for the network for the prediction to turn on. I'm sorry, for the prediction to happen. Alright, I forgot to share this tab. Alright, so now you can see here that I had actually forgotten to change the tab. I'm sorry about that. This was the linear regression code. This is the part where we define the loss function, which I just explained. Alright, and this is the part where we actually run the algorithm, and we run it for 200 iterations. We are just giving it the x values, the y values, and the code for linear regression. This is a network which it will train on, and we just give it and make it train. That's it. Here, so after the training has completed, what we're doing is we're writing plt.scatter. Once again, we are plotting the values, and we are plotting the line for every single x batch and y batch so that we get this straight line out here. So as you see that this code in TensorFlow 1.15 was quite long, and although it does give you a very good understanding of how linear regression works, this could be much simply written in TensorFlow 2.0 using a simple single perceptron layered neural network. So what's a single perceptron layered neural network? It's just a cool name of saying, or a cooler way of saying, we have just one neuron. What does a neuron do? It takes in some weights, it takes in some inputs, it trains it, and it learns some weights and biases. That's it. So a single neuron will learn that many number of weights as for every input. Say for one prediction, it has 5 inputs. So your your single neuron will learn 5 weights plus 1 bias. Now, for our x and y prediction, every single input, we have just, for every single output prediction, we have only one input. Say our input is say 1, as we just showed you in the example. Say your input is 1, your y should be 1.15 into 1, that is 1.15, plus 0.5, that is 2, plus some random noise. So your output should be around 2, plus minus 0.2, because that's, only plus 0.2, because it's always, this noise is additive in nature. Alright, so let me show you how we can train a neural network with just one single perceptron and get the same sort of results. So all the code which we wrote in the previous slide can be replaced by just this one line here. So this is another notebook which we have in Google Colab called Linear Regression using TF.Keras. And all the code which you have been seeing till now will be replaced by just this one line, where we create one single neuron. The way we create a single neuron in this Keras is a framework over TensorFlow to make programming with neural networks easier. So we see that it has just one neuron. This is the shape, and we are defining the input shape as well. An optimizer is something which is used to train your neural network. Just like in the previous example, we are using SGD optimizer. Here we are using Adam. And those of you who train neural networks frequently, for them, a piece of advice here is that if you do not know what optimizer to use, always go with Adam and a learning rate of 0.001. It pretty much almost always works. Alright, so we'll run this cell and we'll write splnn.compile. What this means is that it actually starts defining your neural network, and you have mentioned the loss as mean squared error. We do not actually have to write tf.reduce mean ypred minus y whole square. Just setting up this parameter here will work. Optimizer we already defined above. We are using the Adam optimizer, and metrics are something which we will try to reduce and which would be visible as we are training as well. So let's run this algorithm, and I'll actually show you how the training would vary between using a single neuron and using multiple layers of neurons as well. Alright, so it looks like our training has completed. Yes, so our training has been completed, and we see that we got a mean squared error of about 0.3W. So from this line here, we can see that we created a neural network this time, and even in the previous example, we had actually created a neural network, but it was just a more longer version of writing it. Here we created a single neuron, and it's learning two weights for every output, the weight and the bias. That is for your x variable, what will it multiply it with, and what number will it add it to, the w and the v. All right, and we can actually see what weight and bias has been calculated by the neural network as well. In Keras, we have something called dot trainable variables. So if you type in splnn, the trainable variables, you can see that the variable called w is a NumPy array which has the value 1.510688, which is very close to 1.5, which is a target. And the bias is about 0.487 because the weight was a bit more, and it's actually trying to incorporate the noise which we have added as well. So since it's additive noise, we expect the weights and the biases to be slightly higher than the actual values which we calculate. Now we'll actually be using a multi-layered neural network. So in this neural network, we have just one neuron, one layer, one neuron, and that's it. But we can also create a multi-layered neural network. So what we do here in Keras is that, imagine we have 64 neurons in the first layer, and we have 64 neurons in the second layer, and one neuron in the last layer. This one neuron is just a sigmoid activation layer, which will just say if it's, I'm sorry, it's not sigmoid, I misspoke. It's just a simple neuron which will just give a value. Now here we see something called activation as tf.nn.ReLU. What ReLU activation is in a neural network, some neurons would get activated and some neurons will not get activated. So how do we actually understand that whether this neuron has been activated or not? If a certain condition is met, say you could simply visualize it in this way. Imagine there is an activation function called less than 10. So if you give an input of say 1, it should return true. If you give an output, if you give a number as input, which is 7, it should also be true. If you give an input of 100, it should be false. Similarly, for every single previous number in the neural network, the next value would be calculated based on this activation function. So we have 64 and activation as tf.nn.value. So our neural network would look something like this. I'll again share the tab here. A neural network will look like this, but instead of visualizing them as these rectangular boxes, please visualize them as a single list, like one list which has 64 values in the first neural layer, 64 values in the second neural layer, and just one single neuron in the last layer. So it's all one dimensional. Alright, so now let us go back and train this neural network. We are using the same compilation parameters here. The loss is mean squared error, the optimizer is optimizer, and the metrics is mean absolute error and mean squared error, and we'll fit the neural network. And yes, one more interesting thing here is that unlike our previous example in which we created 100 values between 0 and 2, this time our list includes 1,000 values between 0 and 1. For everything on this notebook, we have used 1,000 values equally spaced between 0 and 1 as a training data. Alright, so our training has completed, I think. Yes. Alright, so now let us actually try to predict the values using some neural both of these algorithms. So let's try to take a value like 5896. I'll make the screen a bit bigger now. Alright, so you see that our x is 5896 and our target y is 1.5x plus 0.5 and some extra noise. Uh, Alright, so we'll print the actual value and the predicted values. So our actual value, which is a target, is the 8844.5, and our multi-layered neural network, which we call it regressor, gave an output prediction of 90.48, and our single perceptron layered neural network actually fared better, and it gave an output of 89.07. So this is what I was actually trying to show here, that just using one single neuron turned out to be better than having a bigger neural network. The reason here is that because we have a simple data set and it can be easily, like it's a linear transformation which can be done with one neuron. So the single perceptron layered model actually fared better. But given enough training, the multi-layered neural network would definitely be able to reach this accuracy as well. But that would require a bit more training. So let's try to predict it for another value, say 2000. Once again, we see that a single perceptron layered neural network, as a single neuron actually fared better. Let's take a value 2. Here as well, the single perceptron layer neural network fared better. Now let's actually go back and train our regressor for a few more iterations. Say instead of 500 epochs, let's train it for 1,000 epochs. And by the way, the training which has been done till now will be safe. It won't be like it will forget everything and reinitialize everything from scratch. It will just train it for a few more epochs over what has already been trained. And unless something goes massively wrong, like the recording has some issue or there's some technical glitch, we will definitely be uploading the recording on GitHub. I'm sorry, on YouTube. So you can check it out as well later on. And if you have any questions, you can ping me on LinkedIn or any of my social platforms as well. I'm not exactly sure what happened here, the OSNAP symbol. Let's try to see if the training happened or not. All right, it does look like the training. You see that the regressor has improved its accuracy a bit. Let's try for some other value, a bit bigger value. Yes, the regressor, at least the error the regressor was making, it was giving much more bigger values initially. Now the values are comparatively smaller. So it does look like the network has improved somewhat. But one thing here is that if you try to actually go back and analyze, if you try, just give me a second here. I'm not sure if this training actually happened or the server crashed or something. It's the same training didn't complete yet, I think. So it's 3.5 tomorrow. All right, let's check it out. Probably the server crashed. I'm not sure about it. I don't actually remember the previous value, but it should definitely not be the same value. So if you saw that the value was same, then yeah, training did not complete. And this is the first time Google Colab crashed on me, so. Alright, it's almost done. Yes, training definitely completed this time. And I actually forgot what value was here. For 2, I think. For 2, right? Yes, I remember this time. It was 3.51. So from that, it has become 3.46. But it does look like we stopped at an inopportune moment. 1,000 is a big number, so it might. Yeah, anyway. So now we see that the regressor has actually decreased a bit to 3.46. So the error looks like 0.4 for the regressor and about, it's very minute for the single perceptron layer neural network. So it actually became worse. Neural networks are massively stochastic. So stochastic means it depends on where you are starting from or what sort of path the neural network is taking. So it could just be like it got unfortunate this time, but a bigger neural network would always be able to replicate the effects or the prediction power of a smaller neural network. This is a known fact, but how long it would take is questionable. Like a bigger neural network would take longer to train. So for example, for a smaller neural network, the single perceptron layer neural network, I could train thousands of epochs in a very small amount of time. But for a big network, that would not be true. Alright, so coming back, we cannot actually visualize the, see, for SPLN and the trainable variables, you can easily visualize the 2 ways which it is learning. Alright, when it crashed, it actually lost all its previous variables as well. So anyway, we had already seen that there are 2 weights which single perceptron layer neural network learn, the weight and the bias. Is it possible to have a look at the history of the training of the regressor? Yes, it is actually definitely possible, because I think we saved the history here. But for that, I will have to just write some code. it's not massive. It's very easy to do. I think you can get back to me after the workshop with this. I can maybe even in my GitHub I will add the code so you can visualize training as it proceeds as well. I think that should sound good. For now, we can see the mean squared error and the mean absolute error for the SPLN and the regressor here. Alright, so if you type regressor the trainable variables, it would actually give you the outputs for the 64 rows in the first 64 weight matrices for the first value, then the 64 neurons would each be learning something from the previous values, so that would be 64 into 64 values. So yes, so there you will have 64 squared values. There would be a lot of values which all of which we would not be able to actually read and comprehend. So it would not be something simple as 1.5 and 0.5. We could just as well train the SPLN once again. Because it's a small neural network, it won't take much time to train. So I can show you the trainable variables differences here. So you see, when you see the things which the SPLN has learned, it has learned just these two weights, the weights which I'm highlighting with my cursor here. But the regressor neural network has learned all these weights. So it's a bit more difficult to exactly understand how it's working. Alright, so with this we come to an end of the demonstration of linear regression, trying it out in 3 different ways. I already shared the notebook with you. So if you have any questions, if you want to try it out a bit more at home, do feel free. Feel free to ask me any further questions later on as well. Right now we'll quickly move on to the demonstration of classification. Do you have any questions still now? I think Matthew already answered your question about seeing the history. You can see the history, but typing it out right now would take some time. Not much, but I think it would be better if we do that later on after the workshop. And regarding database feature activation, let's start sharing this tab. By the way, I also give you my LinkedIn here, so if any of you have any questions, you can directly contact me over LinkedIn. Perfect. So in this notebook, what we are trying to do is, we already know how to classify between a cat and a dog, but we do not know exactly what the neural network is looking at each particular part of the, or at each particular layer. So that is something we are trying to do here, to see what the neural network is seeing. We'll first of all download the datasets. This code is adapted from Lawrence Moroney's TensorFlow Interactive Specialization. And he has also designed this horse versus humans dataset. So in this dataset, there's actually no real humans photo present. All of them are computer-generated humans, which makes it all the more interesting. Like using computer-generated humans, we can train a neural network which can identify real humans as well. The horses are real. In the dataset, the horses are actually real horses. And in this part till now, what I have done is I have downloaded the dataset. I have extracted the pictures into folios, horses, and humans. Now what I'll do is I'll create 4 directories for horse names and human names. Horses which are training as train horse, horses for testing which are validation horse, humans which are training as a train human, and humans for testing as validation human. So these are just defining their paths where these images are present. And now we can calculate how many horses are there in the data set and how many humans are there in the data set. So we have 1027 horses and 256 humans in our data. I'm sorry. We have 1027 training images and 1256 testing images. In this notebook, our goal is actually to visualize what the neurons are learning rather than get a very high accuracy. So we'll be training a very small model. We won't be using anything like dropout or batch norm, etc. We'll be creating a simple neural network with some convolutions and some max pooling. So here we are defining our model. Convolutions are a sort of convolution layer is a layer. It does this operation. Say you have, let me actually bring up a site which shows convolutions. Just give me a second as I look for a. Alright, so if you look at the top right of your screen, you can see that we are picking up the first 3x3 part of this matrix. We are multiplying those 3x3 values with another matrix which is 3x3 in size, element-wise multiplication, and we'll store that result which we get in one cell, the final cell which we have in our. So this is how your data size will also decrease as you're doing a convolution. You can actually keep it constant if you add some padding. We won't actually go into detail about how convolutions look like or how convolutions work mathematically, but this should be a good enough demonstration in which like you pick up some values. It can be 3x3, it can be 5x5, and then you multiply them element wise, and then you take their sum and store the output in your result. Alright, so I hope this is clear. In case it is not, you can ask me right now. If you want me to explain convolutions in more detail, you can ask me right now. I actually just want you to see how the neurons actually work or what they see at each particular layer, and not focus more on designing an efficient neural network right now. So you assume that it's an operation which is done in machine learning and since it's two-dimensional, just which we saw, the layer is called confluri in Keras. So we create 16 of these neurons in the first layer, all of which are of size 3x3, the exact same thing which we just saw. We are using the ReLU activation function. So we have 3 layers in our neural network. Everything else is pretty much commented out. In Python, this hash symbol means commenting out. Alright, so we can see a model.summary which will show how many neurons are there, what the shape of each layer is. So we can see that the first confluri has 16 units. Then we have a max pooling which is 16 units. So if you go back to this figure to explain what max pooling is, so imagine that in place of this other matrix which you have, you just pick up a 3x3 matrix and you pick the highest value that is there and you place it in this final result box. Next, you choose the next 3x3 block. Again, choose the maximum value and place it in the result box. So that is max pooling. So now we can train our model which we just designed. And this is, by the way, how you can plot your history. When you're running model.fit, if you want to visualize the history, do not just call your model.fit, assign it to a variables, because your model.fit function actually returns some values which can be visualized later with the when you're trying to use this history. History, you can call it anything, but the outputs of your model.fit method would be stored in this history variable. Alright, so we have done like half the training, and we initially started with a loss of about 67%, and actually calling this a percentage is wrong. It's just a value. Initially, our accuracy was about 50%, and now it's about 83% after just 780 pokes. This is pretty good. You see that the accuracy keeps increasing and decreasing. Like initially it was 50, then 87, then suddenly decreased to 67, then it became 82. So yeah, machine learning is still massively stochastic, and there would be some epochs where your algorithm is seeing the data, which is very much similar to your validation data, and it's learning something which is correct, and sometimes it will learn something which is not so much correct. I think, yeah, this is the last epoch. And we will actually be testing our machine learning model on both the images which are there in the test set, and we will also upload some images of our own to visualize them with our own images, so that we are sure that the model is actually working as expected. So I have four images of horses and four images of humans. So I've named them horse 1 to horse 4 and human 1 to human 4. And I'll actually show you what my images look like. So these are the four horses which I took. You can see that I took quite a good variety of horses. So one of them is a normal horse, which is on its rear hind legs. One of them is a picture of a horse, which is more of a cartoon. The third horse is actually a human sitting on it, riding it. So this could also be classified as a human because the legs of the horse seem to be in a good position for maybe the human as well. And we'll see what the neural network predicts it as. And the fourth image is that of a group of horses. And let's see the humans as well now. One human in the first image is of a guy whose back is faced. The second image is of a girl standing next to a mirror. The third image is of some village ladies who are collecting pots on their heads. And the fourth is of a party. So alright, I'll go through this code line by line. For every single file which I uploaded, I'm assigning it a path. Then I'm reading the image which is there at that path. I'm again resizing it to 150 cross 150 because that's the input size for a neural network. Then I'm converting it to an array. What ing to array does is say an image is when it's read, it would be in a certain format, so that has to be converted to an array. And we are plotting the image with x by 255. And finally, we are predicting for each of the images which I just uploaded. So the horse 1 to 4 are all predicted as horses, and all the humans are also mispredicted as horses. Alright, this does not usually happen. We always have some horses which are mispredicted and some humans which are mispredicted. In this case, all the horses are correctly predicted. It seems like the neural network has learned that everything is a horse. I'm not exactly sure why this has happened. And instead of going back to the rest of our demonstration, let's actually train the neural network for a few more epochs. Because it seems that the neural network stopped at a very bad position. Not really sure why this happened. Alright, so let's train that for 2 more epochs. Or it could just be that the images which I chose happen to be confusing for this neural network. That could be the case as well, but that does not look very feasible. So, stop this thing. Alright, let us go ahead and look at why it's predicting it as a horse, why everything is being predicted as a horse. Rather, let's so now what I'm going to do is I'm trying to read some human images from the human test image directories, and I'll try to predict what it is, what the neural network thinks it is. Alright, so it is not that the neural network is blindly calling everything a horse, although it does look like this from the 8 images which I have here. We'll now explore why the neural network is going wrong and where it is going wrong. Let's try this a few more times. So we'll have another human which we have selected now. Alright, so this is what the human looks like, and as I said that all the human beings here are actually cartoons, so all the humans here will look like cartoons obviously, but it's at least giving you a correct prediction. Now let's randomly choose between a horse and a human. Now you can also get a horse and also a human, even we do not know. Let's see what picture we get and if the machine correctly predicts it. So we got a human and it's predicted as a human. Let's run this once more. Alright, so the horse is also being predicted as a horse, which is pretty good. Now for this image, let us look at what the neural network is looking at. For every single layer, we have 3 main layers and 3 max pooling layers. So let's create a visualization, which has been done here. Alright. Let me, instead of presenting my Chrome tab, it's present my entire screen. So the presentation will stop for a little while. Alright, so this is what the first layer is looking at, and you see that there has been some edge detection in some of the layers, and you see that the background has been hazed out in some of these pictures here. Say the 4th picture from the right, their background has been hazed out, so the neural network is actually focusing more on the horses. Alright, let's look at what it the algorithm is looking at in the last layer of the neural network. So we see that it's still focusing on the lighter portions are where it's focusing on, and it's focusing on the edges of the horse and where the horse are in most of these neurons. So it does look like it's correct. And yeah, let's choose an image. Say let's pick up human 2, which was mispredicted, and let's try to visualize and see what it's being predicted as. So this was predicted as a horse already. Let's look at where the neural network is looking at for every single of these layers in the neural network and see where it's going wrong. For example, we can clearly see that in the first layer, it's looking at all the right places. The girl's hair, the head has been clearly bifurcated. The face has been bifurcated. But let's see where it got wrong in the last few layers. This would be corrected by more training, definitely, because the first few layers are going pretty well. So the last layer looks like pretty much noise, so it probably did not know anything about what it's seeing. Now we can actually pick up another value, say human 1. And it's predicted as a horse. And if you want to check like how it's making this prediction, you can check this from the visualization here. I would take a minute to actually explain this visualization as well, what we're doing here. Now let's zoom in on this. All right, it does look like it's focusing in the right places, but more on the ground underneath the human and not on the human itself. But the human's figure has also been clearly identified. Going back, like what's so interesting about this visualization is that we can, as we already saw, we can using Keras's inbuilt functions, we can see what the neural network is seeing at every single iteration. You can see those weights. So we are using those weights to create to generate every successive input, and we are using another visualization model to predict it. Since we are running short in time, I would be explaining this would take a little time. Feel free to actually take this code and change these values 64 and 128. It will still work. For example, I can try the value 126. These are mainly just used for contrast in the values. Otherwise, a lot of values would go out of range and you would see these black squares. So let's see a horse image, which was correct. And you can see that the boundary of the horse has been clearly identified or demarcated, and even in the last layer everything is clear about the horse. So the reason why this sort of visualization is helpful for a machine learning practitioner would be you can easily add it into your training pipeline. Like you do not have to change the code in any way. You can simply copy paste uh, this cell which I have from this let's define a new model to this Viridis CMap Viridis, which is basically the color map. You can change it to gray to see everything in grayscale. You can put this code in your pipeline to visualize where your neural network is seeing. For example, imagine it's classifying a horse as a human, and if once you see this picture, you can actually understand that okay, so this is a pattern, or this is where the neural network is paying attention, and we have to give more training. So this pattern is not classified as a human because it's actually the picture of a horse. So it gives you a better insight into how your neural network is training. It can also make your understanding of your neural network faster. It gives you a bit of confidence, like, okay, so this is what the neural network is doing because this is what it's seeing at each and every layer. There are also much more sophisticated methods than this, like CAM, GradCam, plus, etc. You look them up as well. If you want more resources on those, you can ask me on those social media links which I have just shared, LinkedIn, Twitter, and GitHub. Feel free to ping me up. I did say that if you have any more questions, you can ask me after the workshop. With this, we come to an end of both the demonstrations of today's workshop, so feel free to ask any questions if you have. Alright, it was amazing being with all of you in this demonstration. Thanks for being such an amazing audience. In case there are no more questions, I'll wait for a few minutes for any further questions. If there are no more questions, we can uh, close this presentation.